Good morning, everybody. Yeah, it's an honor and a pleasure to have this chance to talk to you all about my thoughts on intelligence. You know, it's something I've been working on my whole life. And yeah, I want to share it with you. So I'm going to talk about intent. I'm going to talk about experience. And let's start with experience. So experience, yeah, actually I want to start with a little bit of an outline or summary. And you know, if you want to take just a little bit of nuance, the one technical nuance, but it isn't really technical. It's just conceptual nuance. To reinforcement learning and machine learning, the first bit of nuance you should try to pick up is to distinguish between the problem being solved and the methods for solving it. Because you might think that a lot of disagreements about, oh, you should solve this way, you should solve that way. No, most of the biggest disagreements are about what problem to try to attack. And so like reinforcement learning is first, it's a different problem than supervised learning or next token prediction. Okay, so today I'm going to divide my remarks into remarks about the problem and remarks about solution methods. Okay, so experience. What is this experience? It's not some fluffy thing or obscure thing. I'm kind of I don't know, in some sense I'm kind of a hard guy think of myself as a scientist, and I'm always searching for minimal explanations. So I'm not going to let in things into my thinking that are unnecessary, or at least I am very hesitant to do that. Okay? And so one question is, do we need intent? Okay? What is this new idea? What is this different idea? And yeah, I think we actually do, but I'm bringing in with some hesitation, and so I have to have a good reason for it. I have to have a good engineering AI reason. Now I'm going to show you some things that are sort of biological or natural, but I'm not trying to make something like nature. I'm being inspired by nature, but I'm constrained by the engineering of the problem and the computational resources, the need to do things efficiently. Okay, so what is experience? If it's not fluffy and obscure and touchy-feely, it's the actual data that the agent will have during its normal life, during its interaction with the world. So another way of saying it is that experience is those sensations and the actions. Sensation is another word for observation. Observation, sensation, the input bits and the output bits. So here's our agent, input bits, sensation bits, action bits. And that's a bit abstract, you know. So I need to show you a video so you know what I'm talking about. So here's some videos of agents, people playing a game or talking to each other or animals living their lives. And so what do you see? I think what I want you to see is that minds are this high bandwidth information processors. Things come in and things go out. Number one job of a person or any agent is to pick its next action. And it's got to be focused on doing that. So it's generating the stream of inputs, or the world is generating the stream of sensation bits, and the agent has to generate the stream of action bits. You might also notice that a lot of what's going on here is very goal-directed. Like the soccer player is trying to evade the other players and then, you know, make a literal goal. Like, there he goes. That's messy, by the way. You know, obviously the baseball player is trying to hit that little ball. It's racing at him so fast, or decide not to swing. Okay? It's a really high bandwidth, rapid information processing task. And same for the animals and for the people having their conversation. What is going to be the goal there? What's going to happen? We don't know. Okay, so these are these bits going in and out, and they're going in and out to the world. And the world I like to draw as a very big thing, because the world is massively big. compared to the agent. And that has to be taken into account more and more. We call it the big world hypothesis. But anyway, the bits are going out coming from the world, going back out to the world. Oh, there's DJ. I think he's going to be able to give his talk this morning. Good. So the agent just sees the bits. I mean, by definition, it sees the bits coming from the world, it just sends bits. So its knowledge of the world is really knowledge about these bits. And that's all it sees. It's just bits in and bits out. So for the agent, only this experience is reality. It doesn't think about, it doesn't have access to the world. All it has access to the bits. And so if everything else is really a story. You might think the world consists of objects and people and space and geometry and, I don't know, chickens and poutine, all those things. Those are just a story about the bits that you've received. So one way of saying it is that everything you know about the world is a belief about your experience bits. And this is a beautiful way to think, because if this is what it is, then you can test it. You can live your life, and you have a belief about what will happen. You'll see if it does happen. So unlike, for example, a large language model, an experience-based agent can tell if it's right or wrong, if its beliefs are right or wrong, because it can compare them to the data coming in during its normal life, whereas a large language model can't learn after it's been created, because it no longer has the supervision from humans. Okay, so this is the experiential mindset. That's all about bits. So, yeah. One more, it's just such an important point, I want to dwell on it. One consequence is that, in a conventional way of thinking, your data can be incorrect. You might have mistaken data. But in the experiential way of thinking, it can't be. The data can never be wrong, and the data is the ground truth. What can be wrong is your theory of the data. Your prediction of the data might be wrong, but the data cannot be wrong. So everything you know is a belief about the bits. In particular, it's a prediction about future sensation bits, how they might depend on your action bits. Okay, so yeah, the experiential mindset. Experiential mindset is just that, the agent is intelligent to the extent that it can say things about its input bits. So what can you say about them? Well, you can predict them and you can control them. Particularly, you might want to control your reward. Your reward is just a designated sensation, a designated signal coming in from the world, or some part of the world. Of course, in people or in animals, it's coming from a particular part of the world that's inside the animal's brain that computes the reward signal. We still consider that outside the agent, even though it's inside the animal. Experience, then, is the focus and the foundation of all intelligence. And a little bit of historical, who first thought this way? Okay? And actually, it was Alan Turing. This is Alan Turing, a quote from Alan Turing's paper and talk from 1947. There was no AI then. As far as we can tell, this talk was the first public presentation of AI, 1947. Okay, so let's talk about the trends of the field. This is the chronology that AJ put up. So right now we are still in the era of human data, and where all our AIs are trained on human-generated text and images. It's fine-tuned by humans, experts, and it's trained in many cases to predict humans' next words or to predict human labels, not to predict and control the world. This is the era of human data. But I think we're gradually reaching the end. We're starting to reach the limits of this human data. And most high-quality sources, like from the internet, are used up. They've already been consumed. And generating genuinely new knowledge, it's beyond this approach. Like, we are mimicking people, and people are intelligent. And so that's what we're trying to get intelligent by mimicking people. But we don't have people created this knowledge. They didn't get it by mimicking themselves. We need this ability to create new knowledge, and then we need to learn it and disperse it. Okay, so the era of experience, the idea is that experience can provide a data source that's unlimited and can provide new things. So no static data set is sufficient. No static data set. You realize that's what conventional machine learning works with. You have a data set, it's static. And, well, let's look at the kind of data you can get. I mean, we'd like something like self-play. You've heard of AlphaGo learned by self-play. It had a certain level of skill, and it played against itself, and it got better. And it was really nice because it didn't start by like playing against the world champion. Playing against the world champion, it would just lose all the time and wouldn't be able to learn anything. But by playing against itself was about the same level as itself, okay? And so there was a good gradient, and it could tell. Sometimes it would win, sometimes it would lose. Or one copy of itself would win, sometimes the other copy would win. So we'd like to have the same sort of thing for life. Can we get something like for life, that the data set or the experience that we get is appropriate for our level of knowledge? And I think experience can do that, and it's suggested by this video. Okay, so this is a video of an infant, obviously infant, playing with its toys. It's a little bit sped up, okay? But what you see is he's interacting with various toys, and he interacts with each one for a while, and then he gets bored with it, and he moves on to the next one. And so what he's doing is he's structuring his experience to match. You know, he learns a little bit. Maybe all he gets from this toy is that has an interesting color, or it makes an interesting sound. And but later he may come back to that and learn something more. So this is, well, what we're talking about now is curiosity and exploration and discovery, okay? So I think we can imagine how, at least in animals, this is important and this happens, and this brings the experience is now appropriate for the agent's level of understanding, if we can do this. Okay, so this experience is the way people and animals learn. It's the way AlphaGo learned to make its creative move number 37 that won the I think it was the 4th match and demonstrated true creativity. It's the way other systems, the AlphaProof system that also from Google and won a medal in the International Mathematical Olympiad. This is the picture. Let's look at it one more time. We're detecting 3 eras just in recent times where we have this changing level of excitement and attention to the reinforcement learning ideas. And going from left to right, we have the Atari using a reinforcement, DQN used reinforcement learning to play Atari that really triggered the modern era of industrial excitement about AI. At the time, it led Google to purchase DeepMind, acquire DeepMind for I think it was $500 million, which at the time seemed like an incredibly large amount. Okay, and now OpenAI is worth $300 billion. But half of $1 billion, $500 million, half of $1 billion seemed like an incredible, extraordinary amount to pay at that time. Okay, so we're talking about curiosity. I'm really getting into the solution side. The problem is about whether we want to talk about the era of experience, reinforcement learning, and the solution is we use curiosity. And in some sense, I can end here. There's one more idea, and that is that curiosity works much better if there are many goals. So you think of the infant playing with its toys. It wants to understand each toy. He finds a red object. How can he control the red object? How can he predict what sound it will make if he hits it, or how it will move if he applies forces to it? So you have many, many goals, and this is something that the minimalist in me might resist for a while, because you notice reinforcement learning has only one goal. It's trying to maximize reward. And so the big question is, and I think we're going to come back to it several times today, is there one goal or are there many goals? And it seems contradictory to think, my remarks may seem contradictory to you. Reinforcement learning, the problem says there is only one goal. But to solve the problem, the agent creates sub-problems for itself, like how can I control this object? How can I get the red to come back? How can I make the interesting sound to happen? How can I get up a podium? How can I find the restroom? How can I travel to Toronto? How can I learn to play soccer? We have many, many sub-goals throughout our lives. And why? You know, the question is why. The minimalist in me, the scientist in me, asks why? We have one goal. The goal is reward. Why have sub-goals? And the answer is that we need a higher level of structure in the mind. The mind can't just work with actions. Actions are low level. Sensations are low level. We need a higher level of structure. And this has been known sort of for a long time. So let me just skip over some pictures of animals playing and give you point out this list here of this long history in AI and reinforcement learning of looking at sub-problems as that are distinct from the main problem, and curiosity, intrinsic motivation, auxiliary tasks, and there are three key questions, but the one that I'm trying to focus on is this last one. How do sub-problems help the main problem? Because they're not the main problem. So why do we do them? And there are three reasons that have been offered, and yeah, I mean, so I don't want to go into the detail, and I don't have any time at all. I have zero time. But I want to point out that this is something that the field has been focused on really for a long time. How do we have sub-problems? How does the agent learn to think at this higher level? How does it use the sub-problems to plan at a higher level? And this is what we mean by intent, although the field hasn't yet used that as a word for focusing on this idea of sub-goals and learning about sub-goals. Okay, so yeah, I guess I do want to say one more thing, which is this notion of, well, let's say you've learned how to do all these various different things. Now I can get up and down from the stage, or I can find the restroom, or I can go to CDL. I can do all these things, and then I have to decide, switch among them. And maybe when I look inside the brain with neural fibers and look at the signals going in there, I'm hoping to look at the level of these sub-goals. And so we have developed, several people have developed, Doina Prekup and some of her students have developed this idea of the sort of a keyboard where you touch to say, I want to achieve this sub-goal, I want to achieve that sub-goal. Maybe I hit a chord, and it means I want to achieve both of these sub-goals at once if possible. And so this idea of a sub-goal keyboard is another existent idea in the field that I think pertains to this novel thing that we're going to talk about today, which is how we can interface our minds to the computer and augment ourselves. Okay, so in summary, we're entering the era of experience. I think in that era we have a single goal, the reward, but we need data, we need curiosity, and curiosity works much better if there are many goals, which also enables action at the level of sub-goals or intent. Thank you very much.